So Cynthia's been talking about the theory of classification, and specifically she's been talking also about logistic regression. So in this video, I'm going to show you using some R code, a simulation in R, some of the properties of classifiers in general, but also of logistic regression. All right, so let's have a look at some R code. So the first thing we're going to do is simulate some data. And we have a label, which we're going to call Z, which can have either a true or a false logical value. And the features, which we're going to call X and Y, which is going to have two features in this case, are going to be generated from random normals. And they're uncorrelated. So very simple case here. And the centroid of the true cases is going to be 1, 1. And the centroid of the false case is going to be -1, -1. So let me run that, and you can look at the head of the data frame. And as advertised, we have our two features, X and Y, with some various random generated values. And we have our label, true or false. And let's just look at an XY plot. So there's no trick here. This is just simple ggplot2. But I'm going to make the color of the point I plot based on that label Z, true or false. So there you have it. So we have kind of blue-green true and red false. And you can see there's some overlap. There's some red points that are clearly getting up into the blue zone and maybe a few blue-green points that are getting into the red area. So no matter what classifier we use, given this overlap in the feature sets, we're never going to get a perfect result. And as you recall, Cynthia talked about this logistic function. So let me plot that. And all I'm doing here is I just compute that. Remember, it's just the exponential of x over 1 plus the exponential of x is one way to write that. So I'm just creating 100 values of x and then 100 values of y and just plotting them for you. So let me run that. And you see the plot here. And so what can you see? So you see this sigmoidal logistic function here. And you have this decision threshold at 0. So I've made this 0.5 right in the middle. So if the result of the regression is more than 0.5, we're going to score that as a positive or a true. If it's less than 0.5, we're going to score that as a negative or a false. But keep in mind, I can move that decision boundary. I can move it down here, in which case I'm going to score more points as true and fewer points as false. Or if I move it the other way, I get the opposite effect. Okay? So let's compute a logistic regression model here. So I've just got this really simple function called logistic.mod. And I'm using the RGLM function. And so I model Z by 0 means no intercept. So it's just x by x and x by y. And I'm going to use a binomial distribution family because it is logistic regression. We just have that true-false binomial output. And then I can predict my score using the predict method on that model. And then I'm going to evaluate that model. So Cynthia's talked about this. We decide whether something is a true, say positive, if Z is true and the score is true, it's true positive. If, say, Z is false, but the actual score is true, it's a false positive, etc. So just simple logic there. And we can count the errors. And then we can plot that using color and now shape to show whether it's an error or not. So color shows us the true label. Shape is going to show us whether we scored it correctly or not. And we compute the elements of our confusion matrix easily enough. And we compute the usual statistics of accuracy, precision, and recall and print those using the usual formulas. So let me run that code for you and we'll see the outcome. So we have this confusion matrix, and you see we're doing pretty well. We've got 46 true positives, 44 true negatives. only 6 false positives where it was actually a negative value and we said it was positive. And we've got 4 false negatives where it really was positive, but we said it was negative. And if we look at our plot here, remember, round are correct, triangles are error, and red is false label, blue, green is true label. So you can see the decision boundary on that logistic function has to run somewhere through here, because we've got like a false here that's a false positive, because it's actually negative, but it's false positive. We've got some false negatives here with these green triangles. But overall, looks pretty good. Now we'll move that decision boundary. So now we're going to look at different probabilities on that logistic function. We've been working with the default of 0.5, but we're going to move to 0.25 and 0.125. So by doing that, we're going to get more true positives, but at the expense of false positives, which is negative values we're going to score as positive. And we're also going to make the problem harder. We're moving the centroids for the true or positive values to 0.5, 0.5, and for the negative values to minus 0.5, minus 0.5. So we're moving the centroids of the feature sets for the two cases much closer together, making the modeling problem. And so we just loop through those probabilities. We compute a model, and we evaluate that model, and we'll just look at the results here. So here's our first case. This is for where we're right in the middle of that logistic sigmoid, and we get an accuracy of 74%, precision of 0.75, and recall 0.72. Notice in our confusion matrix, we still have mostly true positives and mostly true negatives, but we have a fair number of false negatives and false positives. And you can see what's happened because we've moved the data closer together. We've got a lot more triangles here, the red triangles being false positives, the blue-green triangles being false negatives, and you can imagine our decision boundary is somewhere here. So it's moved over, or it's right down the middle. Now let's move it over, and you can see we get a lot more true positives, but look at all the false positives we're getting here with all those red triangles. So if we look at the statistics there, our accuracy has dropped to 70%, our precision has dropped to basically 0.64, but our recall has jumped up to 0.92. And so we have true positives, false positives, quite a few more, but many fewer false negatives. And we'll move that boundary even more radically, and this time, look at our accuracy is down to 0.6, the precision is 0.56, and the recall is really high, 0.98, and we only have one false negative, but a lot of false positives here. And you can see that in the plot. So here's our one false negative, and all those red triangles are false positives. So I hope that's given you some feel for not just logistic regression and how we do it in R, but also how classifiers work in general, and how doing things like moving the decision boundary or playing with other aspects of your classifier can greatly affect the performance that you observe when you're building machine learning models.